let's get started. So yeah, there was a catastrophe this weekend, but I'm sure that you're happy that homework is extended here. So I am gonna extend chapter, I get 19. I might have accidentally said 18, but you know that we skipped that chapter. Chapter 19 homework will we do next Sunday because I want you guys to have a full weekend. I know that a lot of you have commitments during the week, and sometimes the weekend's the only time you can do schoolwork. So it was basically out all weekend. I think their planned maintenance was like Saturday morning at like midnight. And I was checking like every 30 minutes. I don't know about you. You probably weren't, because once you got the call from me, you know, you don't have to check. But I was checking all the time, and I was checking and responding, talking to other professors and my professor's subreddit. We were all freaking out. I emailed our Pearson rep to try to get you guys like compensation for this, because this is an 8-week course. Like, you don't have access to the materials for like a good chunk of time, and it came back undeliverable. So over the weekend, their entire email system was down. Someone said that they tried calling them, their entire phone was down. It was like, yeah, it was bad. But it's actually back up now. So it went back live while I was teaching my previous class. So just kind of to reiterate, what I've promised you here is that I'm gonna move the chapter 19 homework due date to next Sunday, so July 24th. We will probably finish chapter 20 here on Wednesday, so chapter 20 will also be due on in next Sunday. And then our last two chapters, 23 and 21, we're gonna do them slightly out of order, just because there's a little bit more material in 23, and then 21 is like our swan song for the end of the term. Will be due Sunday, July 31st. All right, and then our exam, our final exam, which is cumulative, is Tuesday. So that means our final exam is 2 weeks from tomorrow. And it's at 10 a.m. It's at 10 a.m. It's at 10 a.m. Not 10, like this is 10:30, right? Like our final is at 10 a.m. What time is it at? 10 a.m., not 10:30. Okay. Yeah, so that's what the plan is here. I have not updated the due dates yet. I didn't want to touch anything on Carmen about master. I didn't want to adjust the due dates because I was afraid that it might not come back, and then I might screw with it. So as soon as this class is over, I will adjust the due dates to reflect what I just said. All right? So yeah, it doesn't reflect right now. All right. So that's mastering. We left off talking about electrochemistry and relating this to things you already know from Chem 1210. The idea of our activity series, that when we predict redox reactions that happen in aqueous solution, what we did in Chem 1210 is we said, oh, if you put the metal together with a cation that's lower on the activity series than it, then the reaction will go. So that was kind of just like a redneck way of predicting spontaneity. But how we're going to do it now is actually calculate how does the cell potential change when we have differing materials being having a redox reaction occur. So basically, this activity series is our standard reduction potential table, just without the numbers. Basically, that's what we see here. Things that are really easily oxidized, they actually have really negative reduction potentials. Their E reduction is a negative value, meaning that it's not very spontaneous to reduce this substance, to reduce lithium plus to lithium solid. But what that means is that if we take the reverse reaction, take lithium solid, turn it into lithium plus, so the oxidation version, your sign of E changes within there. And so you get a really positive oxidation potential. In that case, it would be +3. So that's very spontaneous. So oftentimes what we're trying to do, what we did in 1210 is we did a combination of two substances, something that's easily oxidized plus something that's easily reduced, to give us an overall positive E cell potential for that overall cell. So that's just relating it to what we did before. And so we went over review of net ionic equations, identifying oxidation numbers for atoms. It's super closely related to charge of the atoms, and that's going to allow us to predict, okay, what's being oxidized, what's being reduced, what's our oxidizing agent, what's our reducing agent. So that's what we looked at in this example when we take copper solid and put it into a solution of silver nitrate, so silver plus cation. When we look at the activity series, we see that silver plus is here and copper solid is there. So based upon the activity series, this reaction does proceed spontaneously because it fits the criteria for redox reaction. But what we'll see here is this reaction goes forward because it gives a positive E cell or a negative delta G value in terms of spontaneity. And so when we go through the net ionic equation here and identify all the oxidation numbers, again, closely related to charge, we see that copper solid is oxidized. Therefore, copper solid is the reducing agent. Silver plus is being reduced because its oxidation number is going from +1 to 0. And since it's reduced, it is considered the oxidizing agent as well. Based upon this balanced reaction, how many electrons are being transferred from one substance to the other? Can you figure that out? How many electrons? Look at the oxidation numbers. So copper is losing how many electrons? 2, because it's all right. Its oxidation number is going from 0 to 2. Do we see that? So it's losing 2 electrons. Where are they going? Where are those 2 electrons going? To reduce silver plus, but 2 of them, to a silver 0. So in this reaction, how many electrons are involved? 2 electrons. And we'll see that when we look at when we start balancing these reactions. So we never balanced in Chem 1210, but we will balance redox reactions in this class, and it's very systematic, right? It's a very systematic approach. All right, so within here, would combining silver solid and copper 2+ be a spontaneous reaction based upon the activity series? Based upon the activity, so silver solid and copper 2+, would that be spontaneous? Okay, let me rephrase that. If I combine silver solid and copper 2+, will a redox reaction occur? No, because copper 2+ is lower, or sorry, it's that copper 2+, the cation, is higher on the activity series than silver solid. So that's the wrong way to do it. So relating this to this chapter, this redox reaction doesn't happen because the E cell, the cell potential, is negative, or delta G is a positive value, that it's not spontaneous. So that's kind of the leap that we're taking in this, going into more detail with this course. Versus, what if we combine silver plus and copper 2+? Would a redox reaction happen there? No, because they're 2 ions. There's no true reducing agent in this case. So this would also be a not spontaneous reaction, again, because we don't have a metal present. Right? We just have 2 cations within there. So this would also not be spontaneous. And again, both reasons is because E cell is negative, and what we'll get here is that delta G is a positive value. All right. Okay. So let's look at more oxidation states and balancing stuff. So here's another reaction. So let's go ahead and calculate or determine the oxidation numbers for everything. Left to right, zinc's oxidation number is what? 0. Hydrogen +1, yep. +1, zinc 2+, +2, hydrogen gas, 0. So then we track everything. Zinc is, its oxidation is going up. So is zinc solid being oxidized or reduced? Oxidized, because its oxidation number is going up. Hydrogen plus is, its oxidation number is going down. So it is being reduced. Or you can think hydrogen plus is gaining electrons to make its oxidation number go down. reducing is gaining electrons, all right? Okay, so what's oxidized? Zinc, solid. What is being reduced? H+. What is the oxidizing agent? So in this case, the oxidizing agent is whatever is reduced. The reducing agent is whatever is oxidized. The idea here is like the reducing agent is the thing that gives the electrons to the things that is reduced. So it's whatever's oxidized, and vice versa for the oxidizing agent. So in this case, the oxidizing agent is H+, the reducing agent is zinc solid. So do make sure that you get those, recognize that there's a difference there. I could ask you based upon this question, you know, I could ask you what is reduced, or I could ask you what is the oxidizing agent. Both of those would have the exact same answer, depending on how I ask the question. All right, and then finally, how many electrons are involved in this redox reaction? Can you figure it out? Two again. And how I kind of determine that is I just look at oxidation numbers. Zinc is going from 0 to 2+. So it's losing 2 electrons, and that hydrogen plus is gaining an electron, but it does it twice. So it's gaining those 2 electrons and it's being reduced. So there's 2 electrons there. Oh, and then finally here, based on this, the activity series, will this reaction actually occur? So we have zinc solid and H+. So let's look at the activity series. Will this reaction occur? Yes, because zinc is higher on the activity. Zinc solid, the solid is higher than the cation. So the cation is H+. And what we will realize is because this combination gives a positive cell potential. Okay, so let's balance some more redox reactions. So in that redox reaction, or looking at this one, the zinc and acid redox reaction, the idea here with balancing redox is that when we balance chemical reactions, we need to balance the atoms, right? Yeah, we do that, right? Balance the atoms. But what's special with redox reactions is that not only are the atoms, you know, the atoms are making new bonds, but also electrons are being transferred. So we need to balance the atoms, and we need to balance the electrons being transferred in the chemical reaction overall. So what's kind of difficult here is, you know, when we balance this first reaction, you might notice we just put a 2 in front of hydrogen, and this is balanced, but you don't see the electrons in the balanced chemical equation. They're kind of in the background, right? When we look at the oxidation numbers, we see that zinc is losing electrons and hydrogen plus is gaining those electrons. It's all happening in the background. So you don't see it. It's not super obvious. So we use a very systematic way of balancing redox reactions. So this first one, pretty easy to balance. It just works out that balancing the atoms also balances the electrons. This one, try to balance this one, like in your head, like just by changing coefficients. It's a lot harder. So let's look at the systematic way to balance this redox reaction. The idea is we need to balance the atoms and we need to balance the electrons involved in the reaction. So this is much different than how we like balanced combustion reactions in previous semesters. It's a little different strategy. So this is the strategy to balance a redox reaction in acidic conditions. All right. So the first step is you need to identify your half reactions, meaning we separate the reaction that involves reduction and we separate that from the reaction that involves oxidation. This usually requires you to calculate the oxidation number for everything. And then you split them up. Once you have 2 equations, we have an oxidation reaction, half reaction, and a reduction half reaction, then you do one at a time. You balance all the elements by adding coefficients, all the elements other than oxygen and hydrogen. So in like the previous example, we had sulfur and nitrogen, balance those first. Then we will do something special to do oxygen and hydrogen. So once you balance all the atoms first, then you balance oxygen by adding water on the opposite side. Water has 1 oxygen atom, right? But water also has hydrogens on it. So if we add water, we mess up probably the number of hydrogens present on both sides. So we fix that by adding acid, H+, to get all the hydrogens balanced as well. So the order here is you balance atoms first, oxygen using water, and then you balance hydrogens using H+. That's why we call this balancing in acidic conditions. This is the half reaction method for balancing redox. All right, so we've balanced the elements, oxygen, then hydrogen. The last thing, so we've just balanced the atoms. We also have to balance charge when it comes to redox. So the last step here is you count the charges on each side of the reaction, and you add electrons to make sure that each side of the reaction is charge balanced. And of course, we're doing this for each half reaction separately. All right, and so the trick is here, and I'll show you, in a reduction reaction, electrons are always the reactant, because when something is reduced, it's gaining electrons, right? When something is oxidized, it loses electrons. So electrons are what? A reactant or product? If it loses it. It's a product, yeah. So that's how you can check yourself. You know you did it wrong if you go to balance your oxidation reaction, and when you add electrons to the appropriate side, you put it on the product side. Then you know you did something wrong. Oxidation, electrons will always be the product, and if you add it to the reactants, you did something wrong. All right, and so we'll look at examples here. So once you have that, once you have your electrons in the right place for your half reactions, remember, electrons, whatever is being oxidized, those electrons lost have to be the electrons gained in your reduction reaction. So we need to multiply those half reactions by a coefficient to ensure that the number of electrons transferred equal one another. And I'll show you what that means. And then you just add them up and cancel anything that might be remaining on both sides, right? All right, so let's actually just do an example. And the reason is when we balance in acidic conditions, we're balancing H's by adding H+. We'll look at another method to balance in basic conditions. It's actually the exact same 7 steps. We just add an extra one at the end to balance in basic conditions to make it easy for you. All right, so here are the steps. Let's balance this reaction, revisit this one under acidic conditions. So we need to split our half reactions. So I like to just get the oxidation numbers. What you'll usually see is it's like other atoms other than oxygen and hydrogen are usually what's being like reduced or oxidized, unless like elemental hydrogen or oxygen is involved. So what I see here is that this sulfur is -2. The sulfur on the product side is 0. So that substance is being what? Oxidized. And then the nitrogen and nitrate here is +5, and the nitrogen in NO is +2. So this oxidation number is going down, so that's reduced. So the whatever is on both sides of the arrow, on the opposite sides of the arrow, that is my half reaction. So I like to, I don't know why, but I always put the oxidation reaction first. And so you write H2O or H2S. I'm going to just drop the states because I'm lazy. And then sulfur. That's one of my half reactions. It's what's on the opposite side of each arrow when I identified what's being oxidized, what's being reduced. We already have done a billion of those already. So then we look at whatever is being reduced. So what's being reduced? Nitrate, NO3 minus, arrow, NO. I highly suggest giving yourself enough room here. I might have to move some stuff around because we need to balance now these individual half reactions. So let's do the oxidation one first. So what is the first step? We balance what? Well, we balance sulfur first, right? But is sulfur already balanced? Yes, so we move on. What do we balance next? Oxygen. Are there any oxygens? No. Next, we balance hydrogens. We do have to balance those. So how do we balance hydrogens? by adding H plus. So on what side do we add the H plus? The product side. So how many H pluses? 2 of them. Okay, good. All right, so we balance the atoms, but if you inspect both sides of that reaction, the charges are not the same. The reactant side has an overall charge of what? 0, but the product side has an overall charge of +2. So the way we balance charges is by adding electrons. Electrons are negatively charged. So what side do we add electrons to make them equal? On the product side, how many electrons do we add? +2. What I do, and don't skip this, because when I was writing your overview sheet, I made there's so many places for things to go wrong in a balancing, all right? So oftentimes what I'll do, I'll take out that step, is I will actually count the charge on each side. So I'll say, okay, that side is 0, this side is +2, and my little monkey brain thinks about putting negative charge on what side to make them equal. Because sometimes there might be multiple charged things on each side, and it can get quite confusing within there. So yeah, we add 2 electrons. Now is it balanced? Yes, all the atoms are balanced, all the charges are balanced, it's good. Also, to check yourself, we identified this reaction as oxidation. Are the electrons on the correct side? Yes, they are. Electrons are a product. Also, how you know you messed up, if you get to the charge balancing and you see that you don't need any electrons. That's another way to know that you messed up, and that you might need to back up a little bit and revisit the previous steps to make sure that electrons are in fact being transferred. Okay, so the next one, reduction reaction. So steps, we have the half reaction. We balance the nitrogen first, it's balanced. Now we balance the oxygens by adding water. So the reactant side has 3, the products has 1. So we're gonna add 2 waters on the product side. Yeah? So now we miffed up the hydrogens. So how many hydrogens do we need to add? H pluses. 4 on the reactant side. So 4 H plus. All right, so that is we just balanced all the atoms, nitrogen, oxygen, hydrogen. Now we need to balance the charge. Charges can be a little bit difficult. So again, I like to turn on my monkey brain. What's the total charge of the reactant side? +3. Yeah, so there's +4 coming from hydrogen, but nitrate is a -1. So it's a +3. And then the total charge of the product side is 0. And then I asked myself, electrons are negatively charged. So where will I put electrons to make it equal on both sides? The reactant side, how many? 3 electrons. Okay, so those are our balanced half reactions. The atoms are balanced, the charges are balanced. Now to combine it into an overall balanced redox reaction, we need to make sure that the electrons lost in the oxidation reaction equal the electrons gained in the reduction reaction, because there has to be balance of electrons. But if the oxidation reaction only gives up 2 electrons and the reduction reaction eats up 3 electrons, they don't equal one another. So how we get around that is by just multiplying the reactions by a coefficient, and just be smart about it. All right? So how can you make the numbers 2 and 3 equal to one another? Yeah, so multiply 1 by 3, multiply the other one by 2. That's it. All right? So what we do here to combine these 2 redox reactions is I'm going to multiply my oxidation reaction, everything by 3, and then I'm going to multiply my reduction reaction, everything by 2. And then that's how I get everything to be equal. So I'm just going to show the work in doing that. but hopefully you can do a lot of this in your head once you get enough practice down. So if I multiply the oxidation reaction by 3, I get 3 H2S, 3 sulfurs plus 6 hydrogens plus 6 electrons. Then if I do the reduction reaction by 2, I have 2 nitrates plus 8 hydrogens plus 6 electrons gives me 2 NOs and 4 waters. All right, so then these are the 2 reactions we add, but make sure that you cancel things that show up on the same side. So this is allows us to combine these 2 reactions. 6 electrons produced by oxidation, 6 electrons consumed by reduction. So you clearly see how those cancel when we add these up. What else cancels? Some H pluses cancel. So note where the arrow is. I kind of did a poor job here. So my reaction arrow is like, here, I'll do this. Right there. So all of these are reactants, all of these are products. So the electrons cancel, the H pluses also cancel. So all of those 6 H pluses cancel on the product side, but on the reactant side, how many H pluses do we have left? 2. So that becomes a 2. And then don't do waters cancel? No, that's it. All right, so that's our balanced reaction. So rewriting the whole thing, we have 2 nitrates. Sorry, that should be a 3. Nitrates plus 2 H pluses plus 3 H2S arrow, 3 sulfurs plus 2 NOs plus 4 waters. So when you check all of that out, you should see all of the atoms balance, and in the background, the number of electrons balance as well. All right, so that is super systematic. It will work every single time if you do those steps, those 7 or whatever steps. It'll work every time. And then I have some, tips there for you to make sure you're doing it right. If your electrons show up on the wrong side, then you might have done something wrong. All right, so is that the answer? Yeah, look at that. That's our answer. So once we have the balanced redox reaction, we can then go through some of these questions here. What atom is reduced? So we might have to go back and get those oxidation numbers again. So sulfur was -2. Hydrogen was +1. Nitrate was +5 for the nitrogen. Sulfur was 0. Nitrogen was +2. And this hydrogen is also +1, so it doesn't really matter there. So what we're looking at is things that change. And what we see here, the atom, no, that's right. No, that's wrong. This is that. So looking at what atom is reduced, it's whatever atom, decreases its oxidation number. So that is nitrogen, and nitrate is being reduced. The atom that is oxidized is sulfur, because its oxidation number is going up. What is the reducing agent? Is it just sulfur that is the reducing agent? It's the whole compound. So technically it's H2S. That whole thing is the reducing agent. So again, that's whatever is oxidized, pointing to the thing that's oxidized here. And then finally, how many electrons are transferred in this reaction? How many electrons? 6. 6. Where did we get that? The last step when we balanced it. But another way to think about it, like a kind of a cheater way to do it, really the way we get the number of electrons is when we balance it, right? It's that last step, whatever cancels. But there's a trick to doing it as well. By looking at the oxidation numbers. So sulfur, its oxidation number is what? Increasing by 2, right? So it's losing 2 electrons. But how many sulfurs there are losing 2 electrons? 3. So it's 3 times 2 of them. So 6 electrons. And it should match whatever nitrate is doing as well. So nitrogen it's +5 over here, +2 over there. So how many electrons is it that nitrogen gaining? 3 electrons, but how many nitrogens? 2 of them. So see how that's 6? See how both of them, so there's a little cheater way to do it as well. You can try it both ways. Okay. And doesn't that, that matches the stoichiometry that we have within the balanced chemical equation as well. So that's another way to check your balanced redox reaction. Okay, so we're going to do another one. Yes, let's do another one. Here's the reaction. I gave you the oxidation numbers already. Let's balance this reaction. So first step is half reactions. I like to identify what is oxidized, what's reduced. So I'm just going to track these things. So cadmium is going from 0 to +2. So cadmium is being oxidized. And then nickel is going from +4 to +2. So nickel is being reduced. I don't know why, but I always write the oxidation reaction first. I have since like when I was a Gen Chem 2 student. I write the half reaction. So cadmium goes to cadmium, hydroxide. I'm going to just drop the states because I'm lazy. All right. So, oh, and then write my reduction reaction too. Reduction is nickel, O2, arrow, nickel, OH, 2 of them. All right. So first step, balance the atoms. Are cadmiums balanced? Are nickels balanced? Yes, they are. If they weren't, we would put coefficients in front of the things that are already there. So next, for our cadmium reaction, we need to balance those oxygens. So we're going to add water. How many waters do I add? 1? 2 of them on the reactant side. 2 waters on the reactant side. Then we balance hydrogens. So I'd like to take inventory of all the hydrogens. So how many hydrogens are on the reactant side? 4. How many are on the product side? 2. So we need 2 hydrogens, like 2 additional hydrogens on our product side. All right. Okay. Atoms are balanced. Like check your work, like count up your cadmiums, your oxygens, your hydrogens. You're good. Now the last step is to balance the charge. So it's neutral on our reactant side, but it's a +2 charge on our product side. So I'm going to add 2 electrons on my product side. Is that consistent with an oxidation reaction? Yes, it is. Okay. I like to give you checkpoints. Checkpoints. What's a checkpoint? That's right. So now let's do the reduction reaction. So nickel is balanced. Oh, look, oxygen's balanced too, right? There's 2 oxygens in nickel hydroxide. There's 2 oxygens in the nickel solid. So all we need to balance are hydrogens. So I'm going to put 2 H pluses on the reactant side. And now we balance charge. The reactant side has a +2. The product side has a 0, so I'm going to add electrons to the product side, so +2 electrons. Is that consistent with a reduction reaction? Electrons on the reactant side. Yes, it is. Good job. And then you pat yourself on the back that you hopefully got it right. All right, so those are our balanced half reactions. Now to get the overall reaction, we just add them up, but make sure that the electrons match. They already match. We don't have to multiply anything, actually. All right, so basically, oh, now I know why I write oxidation first, because I like to show the oxidation reaction produces electrons, right? It's a product, and that's consumed by the reduction reaction. That's why I like to usually write it that way, because I like to clearly see, like, okay, oxidation is producing electrons, your reduction reaction is consuming whatever is produced, and they need to match. And so in this case, they already match. So we just add up as is. So the electrons cancel, but what else cancels? The H pluses also cancel. So what we see, this reaction is nothing special. It's cadmium plus nickel oxide, nickel 4 oxide plus water plus 2 waters, arrow, cadmium, hydroxide plus nickel, 2 hydroxide. So that's how we balance that reaction. So note in this reaction, look at what we were given originally. All right, we were just given, you know, the cadmium and nickel stuff. But to balance this reaction, all we did was add water, like water molecules, to get it to be balanced. Like this kind of goes against what we thought of what balancing reactions were in Chem 1210 when we just like added coefficients. We actually didn't add any coefficients. We just added water to make it balanced. And how we got that, because that's not super intuitive, but how we got it was through the half reaction balancing method. Okay? Oh, how many electrons are transferred in this reaction? 2. Yes, so you can see it right here. 2. 2 reactions are being transferred. Also, you can look at the oxidation numbers. You can see how electrons are being transferred. Okay, so there we go. Let's do another one. All right, so here is our skeleton. It's not balanced, so we're taking permanganate. We're combining it with oxalate. And note here, you know, just like any balanced reaction, I can ask you stoichiometry questions once you have the balanced reaction. So in this question, so this is a titration reaction where you titrate permanganate, so MnO4 minus, into you know, some substance. So in this case, it's oxalate. And you still have that idea of stoichiometry, the mole to mole ratio within there. But the idea here is that if you just based, you know, stoichiometry based upon the atoms, you might see that, oh, this is like a 1-to-1 ratio, 1-to-1 mole ratio, but that's actually not correct. We need to balance the electrons being transferred behind the scenes in order to get the correct stoichiometry. So that just requires us to balance the reaction. We need the balanced reaction. You might just look at this and be like, oh, 1-to-1, but that's not right. So let's do it. I always like to start by doing oxidation numbers. Manganese and permanganate is +7 because oxygen typically has what oxidation number? -2, unless it's O2, like O2 gas, then it's 0, right? So what you see here, all the oxygen, you have a -8 equals a -1 charge, so manganese has to be +7. You'll probably just memorize that MnO4 minus manganese is +7. It's the highest oxidation state of manganese. And it's actually like the highest oxidation state I ever see, like +7, that's like a lot. It's like a really high charge. All right, oxalate. So this one's a little bit harder. So O4, so oxygen, I like to set up like an equation, I guess. So there's 2 carbons, so +4 of the -2s coming from oxygen equals a total -2 charge. And so I ask myself, what does the oxidation state of carbon have to be? Yeah, so 2C is +6. So that means 1 carbon is +3. +3. All right, next is Mn2+. That one's easy. It is +2. And then CO2, there's -4 coming from 2 oxygens, so carbon here is +4. So tracking those oxidation numbers, oxalate is being oxidized, and then permanganate is being reduced. So what's the oxidizing agent? Permanganate. Yes, because it's being reduced. All right, so that's the first step. Let's do our half reactions. I do my oxidation one first. So C2O4, 2- arrow, CO2. Okay, that's my oxidation half reaction. Then reduction is my permanganate. So MnO4- arrow, Mn2+. Okay, so let's do the oxidation reaction first. What do I do first? Balance the carbons. So I need a 2 coefficient there. Yeah? Okay. Next, I balance the oxygens. Just take inventory here. There's 4 oxygens on the reactant side. How many on the product side? 4. So do I need any water? No. Cool. There are no hydrogens, so I don't have to balance those, thank goodness. So now what do I balance? Charge. So I'm going to add 2 electrons on my product side. And again, ask yourself, is that consistent with what that reaction is? Yes, it's an oxidation reaction. Electron should be your product. All right, next, permanganate. This one's harder. So manganeses are balanced, but then next is the oxygens. So I add 4 waters on my product side. There should be a 4 there. 4 waters. So now the oxygens are balanced. Next I do hydrogens. So I'm going to add 8 hydrogen, H pluses, sorry, on the reactant side. So I did manganese, oxygen, hydrogen. Now I do charge. Be very careful with charge. Take like just half a second and inventory all the charges on each side. So my reactant side has a positive 8, but a negative 1. So the total charge on the reactant side is actually +7. And the product side has a total charge of +2. And then you ask yourself, if I add electrons, how can I make those 2 sides equal? So you're adding electrons to the reactant side, but how many? How many electrons? 5, yes. I think I was writing a key for something for you guys, and I got this one wrong, and it like propagated through the entire thing. Yeah, and I had to go back and fix it. I accidentally put 6. So be very careful with charges because I mess up too. All right, so there we go. We have our balanced half reactions. So now the next step is to combine them so the number of electrons cancel. So I'm going to multiply the oxidation reaction by 5 and the reduction reaction by 2. So then therefore, what number of electrons are being transferred here? N will equal what? 10. Yeah, although it's not asked, that number will come back again and again in later calculations. Oh, I'll point out that this chapter, this one, chapter 20, it's the last like math chapter of this course. Chapter 23 is just looking at pretty shapes. And then chapter 21 is nuclear chemistry. I think everything's a first order reaction. So like half-life calculations. But those aren't bad, right? Okay, all right, yeah, so this is the last of the math, sorry. So we combine these, electrons transferred as 10. So sometimes I cheat and I just kind of write the, what the coefficient would be up top here. So this would be 2, this would be 16, 10, 2, and then 8. And then the oxidation reaction would be 5, 10, and then 10. And then combine them. Because sometimes you need to do this if sometimes there's like acid on both sides of your like oxidation and reduction reaction, and sometimes you need to like cancel them out. But it doesn't look like anything really cancels out except the electrons here. So writing this fully, we have 5 oxalates, 2 minus, plus 2 permanganates, plus 16 H pluses, 10 CO2s, plus 2 manganese 2 pluses, plus 8 waters. All right. So that is our balanced redox reaction. And so how we can actually answer this question at the very end here is just like a stoichiometry question that I could give you in 1210, as long as I gave you the balanced chemical equation here, is recognize that you need 5 moles of oxalate, or if you start with 5 moles of oxalate, you need 2 moles of permanganate to fully, have a full redox reaction occur within there. And it all has to do with the electrons transferred. It's not just the atoms involved, it's the electrons transferred. So to calculate this question here, we're given a volume and molarity amount of oxalate, so we can get a mole amount of oxalate. I'm going to start with 100 milliliters of that oxalate stuff. Multiply by the molarity. I'm going to use millimoles because I'm lazy. So 0.100 millimoles of my oxalate, C2O4 2 minus. But now that I'm in moles of oxalate, this is where I use stoichiometry. For every 5 moles of oxalate, I only need 2 moles of permanganate. So my stoichiometry here, I'm going to put 5 moles of oxalate, 2 moles of permanganate. All right, and then finally just use the molarity that's given here. So 0.100 millimoles of permanganate is 1 milliliter of that solution. So I think if you do that, you only need 40 milliliters of permanganate to actually neutralize 100 milliliters of that substance. So if you did not take into account redox and balancing electrons, you might just think it's a 1-to-1 ratio. Is this a 1-to-1 ratio? No, it's like a weird 2-to-5 ratio. And it all has to do with the electrons being transferred. Here. All right. And so, yeah, this last piece is just utilizing the actual balanced equation that we got, and that you can apply that stoichiometry just like we've done any stoichiometry previously. Cool? All right. Practice balancing reactions. There's a lot of places to go wrong, but it's super systematic, right? So once you learn the strategy, like those steps, then you're good. All right. Okay, so all of those balancings that we did, we assumed it was occurring in acidic conditions, meaning when we balanced it, we had H plus left over somewhere. Like it was happening in an H plus, like it was happening in a solution that had lots of H plus present. That's acidic conditions. So how we balance a redox reaction in basic conditions is we take all the same steps for acidic conditions, but we neutralize all the acid that's present. So this reaction that I have written, it's the same one, but it's in acidic conditions where we have 16 H pluses. So to make it in basic conditions, all we do is add 16 OHs to the reaction. But if we add 16 OHs to the reactant side, we also have to add 16 OHs to the product side as well. So we want to add 16 OHs on this side as well. But what's special on the reactant side is when you add 16 OHs to 16 H pluses, what do you get? How many H2Os? 16 H2Os. So there are actually 16 H2Os within there. So with that, because we've neutralized those 16 H pluses to now waters, note now how both sides, the reactants and products, have waters, so we can cancel some of them. So let's do that. All of the waters on the product side cancels, and I'm left with 8 waters on the reactant side. So the full balanced equation for this reaction in basic conditions will be 8 waters, and then everything else is the same. 2 permanganates plus 5 oxalates gives me 2 manganese 2 pluses. There's no waters. There's 10 CO2s, and then there's 16 hydroxides on the product side. All right, so the big idea with balancing in basic conditions is you balance in acidic conditions first. If there's H pluses left over on like one of your sides of your reactions, you just neutralize that with the appropriate amount of base, but make sure you do it to both sides, and then cancel any extra waters that you may have. So that's it. So it's just tacking on a little step on the end within there. Okay, so there is balancing. How do we feel about balancing? When I taught at Lima, I used to teach balancing in Chem 1210. But it was a lot for them. It was a lot. All right, so that's balancing, where we looked at balancing the atoms, the oxygens, the hydrogens, making sure electron, the number transferred is matching within there. So now we will look at actually constructing electrochemical cells. What do these redox reactions actually look like? I mean, you did some of these, like inspecting the activity series in Chem 1210, where you put magnesium strips into acid and you saw them bubble. So when redox reactions occur, electrons are being transferred, right? Electrons are also electricity, right? The things that power our junk. So we can harness those electrons to do work for us, but we can only do it when we set up our voltaic cell or our redox reaction in a certain way that gives us a positive cell potential. This is essentially how batteries work. Batteries are redox reactions. Although we're not going to be looking at those chapters, basically these chapters that I have taken out here, it's just application of redox reactions. I know it's kind of fun within there. But yeah, a battery is just the same thing as a spontaneous voltaic cell, which we'll see here in a little bit. That gives us a spontaneous positive E cell. When you calculate the anode and the cathode, or the oxidation reaction and the reduction reaction. It's just all kind of encased in one thing, that we're harnessing the spontaneous transfer of electrons from one reaction to another. I like this picture. Did you ever do this in high school or whatever? You never did it? Where you like take a potato and then people say like, oh, you can power, the world with potatoes, but it's actually wrong. What this actually is what you can't really tell is that there's a zinc and copper nail in each of the potatoes. So actually what's happening is a redox reaction between the zinc and the copper, all right? And the potato is just acting as a salt bridge. So we're not actually utilizing the potato for energy. We're utilizing the redox reaction between these two different screws. And actually, if you look up like the demo for kids, like the potato demo for kids, it will say you must have this type of like galvanized nail, like a zinc nail, and you must have a copper nail in order for this reaction to work. All right, that's where the energy, the electrons are coming from, not the potato. Though, when it's just children, they think it's cool. But you guys aren't children, so I don't treat you like that. It's actually coming from the redox reaction. So let's look at voltaic cells and how we can't take the energy coming from these spontaneous reactions and use them effectively so we can do work on our surroundings. So a voltaic cell is a spontaneous cell. That's it. It's spontaneous, meaning if we take this back, and I always keep going back to the activity series because what we're doing is just basically the activity series. When we combined a metal that was higher on the activity series with like a cation that was lower, that was a spontaneous reaction, right? So if I combined zinc solid and H+, that is also a spontaneous, in a sense, voltaic cell within there. So it's the same idea. So when we construct a voltaic cell, there's a couple of components. We need to have electrodes, so an anode and a cathode, and they have to contain, we have to have these solutions that contain the components of our oxidation reaction and our reduction reaction. So based upon this reaction, zinc solid plus copper 2 plus, let's look at our activity series. Would this reaction proceed forward spontaneously? Copper solid and zinc 2 plus. Yeah, sorry, I got it wrong. Zinc 2 plus and copper, sorry, what is it? Zinc solid and copper 2 plus, I'm sorry, there we go. Okay, let's do it. Zinc solid, where are you? Right there. Zinc solid and copper 2 plus. Will that reaction proceed? Yes. So that means that this reaction proceeds in the forward reaction spontaneously, meaning electrons are being produced or transferred spontaneously. So instead of electrons transferring from, let's say, zinc to copper, all right, directly, why don't we just put a wire between those two things, harvest the energy or the electrons being transferred in a wire so we can measure their voltage, and maybe do some work on the surroundings in that case. We're giving those electrons a different pathway before it actually reduces, in this case, copper 2+. So let's write the half reactions for this process that's happening. Zinc has an oxidation number of 0, copper is 2+, and then copper. Oh, wait, no, sorry, 0. I'm going too fast. So I like to write my oxidation reaction first and then my reduction reaction. So what is being oxidized? Zinc. So we have zinc solid gives us zinc 2+, and then there's 2 electrons being produced. And then we do the same thing for copper. So copper 2+ is actually gaining those 2 electrons, and it's producing copper solid. So those are the 2 half reactions. By convention, the oxidation, whatever reaction is happening at the anode, that is oxidation. Whatever reaction is happening at the cathode is our reduction reaction. So I think the way folks memorize that is N-ox, red cat. I still use that to memorize which reaction happens, which half reactions happens at which electrode. So there's an anode component and a cathode component. Anode, oxidation, cathode, reduction. All right, so those are the 2 reactions. So what will this reaction actually look like? So this is what it looks like. Zinc is being oxidized, copper 2+ is being reduced. So this is what the actual reaction will look like. By convention, how we draw voltaic cells like this, where we have like 2 beakers and they're connected by a salt bridge or a membrane, we always draw the anode on the left side and the cathode on the right side, always. I always like to think they're just drawn in alphabetical order. It always goes cathode, anode, always. So that means since the anode's on the left here, all the zinc stuff, because that's what's being oxidized, is in the anode compartment. All of the copper stuff, because copper is being reduced, is in your cathode compartment. So what would that look like? Let's look at the actual half reactions. We have zinc solid and we have zinc 2+. So we need an aqueous solution of zinc ions in this solution. So there has to be zinc 2+ floating around in that solution. The electrode has to be a metal surface for electron transfer to occur. So the best material to make that electrode is zinc itself. Zinc is a metal. So what you'll see here is that rod that you see, that rod is zinc solid. So see how the anode compartment has both zinc 2+ and zinc solid in it. You see that? And so you see the same thing on the cathode side. The cathode side contains the reduction reaction. So what you see is in solution, you have copper 2+ cations in the solution, and then the actual electrode itself is made up of copper solid. So that bar, it's even the correct color, is copper solid. Okay. So that's what the voltaic cell looks like. Both of these compartments are separated by a porous bridge or a salt bridge. What that does is just allows anions and cations to pass through them in order for these solutions to remain charge balanced. And we'll look at the details within there. So let's look through these questions here. So we already answered this. This redox reaction will occur spontaneously according to the activity series. We already got that. Okay. How many electrons are involved in this reaction? 2. Okay. What substance is losing the electrons? So this is whatever is being oxidized. So zinc solid is losing electrons. It's being oxidized. What substance is gaining the electrons? Copper what? copper 2 plus is gaining the electrons. So based upon this picture, let's think about that. Zinc, solid, is losing electrons, and electrons have to travel through this wire. The only way those electrons from zinc can get to copper plus cations, because they are in this compartment, is to travel through this wire. So what we see here is that electrons always flow from the anode to the cathode, as long as you write anode, cathode. Anode is oxidation, cathode is reduction within there. So what direction do electrons travel? It's always anode to cathode in here. So basically we're saying, hey, electrons are traveling from the zinc, because that's what's losing the electrons, and they are going towards the copper 2 plus in order to reduce the copper ion to copper solid. So we see how the electrons, now we're just harnessing the work, the potential that electrons, that movement from zinc to copper, we're basically just harnessing it, allowing us to calculate like cell potential, the voltage coming from this spontaneous cell. All right, let's look at more details about this cell. So we just located where everything is. But remember, a chemical reaction is happening. Chemical reaction is happening. Electrons are being transferred. So we know that electrons will move left to right with time. Oh, I should point out that the anode, by convention, is always a negative sign. I like to think of it as because electrons are being produced there. And the cathode is always a positive sign, because electrons travel in that direction. Electrons are attracted to positive stuff. So that's how I like to think of it. Or cathode, there's a T in it, and so that looks like a plus sign. So that's another way for you to remember that. So that's the direction. It also tells you the direction electrons go. Okay, so since electrons are moving from the anode to the cathode, let's think about this. What happens with time? As electrons are being produced in this reaction, will the mass of zinc solid go up or down? Look at the chemical reaction that's happening. As electrons are being transferred, aren't we pushing the reaction towards the product side? So how will the mass of zinc change? It will decrease, right? Because we are consuming it. Yeah, so it will decrease with time. So what will happen if you let this reaction go long enough, you will see like tiny like divots, like little dents in the zinc electrode form. Actually, side story, has anyone worked on their, does anyone have an electric water heater at home? No? What? No, like the big one in your basement. Okay, so if you've ever done work on an electric water heater, there's a component in it called a sacrificial anode. You have to replace that once in a while, because what that does, it's a place for oxidation to occur. So you're sending a ton of electricity through water, right? To not through water, but there's a lot of heating going on in your water heater. So sometimes when there's too much electricity going on, you might actually split water. What are the products when you split water? Hydrogen gas and oxygen gas, which is flammable. So we don't want our our water in our water heaters to explode. So instead, how to get around that is they have a sacrificial anode within a water heater to allow a place for oxidation to occur so it doesn't split your water and your water heater doesn't blow up. Right? And so when you change your sacrificial anode once in a while, if you ever pull it out, what a new one looks like is, I think it's like this aluminum piece of metal, like an aluminum rod. But after you replace it, after like 3 or 5 years, when you pull it out, it's like all eaten away. And that's because you're essentially allowing a place for electrons to be lost instead of water actually doing it. Yeah. The water will get colder. Yeah? Colder and colder? like a gas one? Okay. So I'm not a water heater mechanic, but I will try. So the sacrificial anode is a large component of the electrical like panel of the whole thing. So if that goes bad, you're actually breaking the circuit. So yes, if your sacrificial anode goes bad, you will not get hot water. Because actually this happened to me as well, right? Where we had to get some replacement stuff for, we got geothermal installed at our house. So they had to drain our electric water heater. And so when they drained it and then filled it back up, it never got hot again. And they realized it was because the sacrificial anode, it was all chewed up. It was spent. But that's its purpose. Its purpose is to get eaten away, to get oxidized away so you don't split water, because that's bad. And so, yeah, that's probably why. I'm not a water heater technician, though. But that is an easy fix, because the guys who were installing our geothermal, that happened, and like I'm pretty sure right away they realized. When I texted them that night, I was like, hey, like we don't have hot water, it never got hot enough, or it was like kind of hot but not really. They're like, oh, let's replace your sacrificial anode. And yeah, oh no, they also had to replace the heating element on the bottom or on the top. So they actually had to do two things, but that's a pretty easy fix. So it looks like your mechanic was just lazy. Yeah. So also, what can happen is you ever go to somewhere and you use the hot water and it smells like rotten eggs. Yeah. Yeah. So that phenomena is when you start reducing sulfur. So that is also an indication that your sacrificial anode in your water heater is bad if you start smelling sulfur. So you might have to change it again. So your water heater at your home, if you have an electric water heater, has it. Gas doesn't. This is only important with like electrical appliances. Also, like if you have a recreational vehicle like an RV that has a small water heater on it, it also has a sacrificial anode. I replaced that one and it was super chewed up. And then I bought the new one and I compared them and I was like, wow, redox chemistry. And I was excited. Okay, yeah, so yes, the mass of zinc will decrease because a chemical reaction is happening. What about the mass of copper? How will that change? It'll increase, yeah. So what you'll see here is that zinc solid, the mass will decrease. The zinc atoms don't go away, they just go somewhere new. Because zinc, how does the concentration of zinc change over time? If zinc solid is being consumed, zinc plus cations are being produced. So won't the concentration increase? So essentially you're going from the solid form of zinc and it's like solubilizing into the surrounding solution. And then kind of the same but opposite happens for copper 2+. Copper 2+ is being consumed. So won't that concentration with time go down? Because it's being plated, those copper atoms are getting plated on the electrode itself during the course of this reaction. Okay, so that's how the components of your different compartments are changing. Now let's look at the idea of the salt bridge. The salt bridge, okay? In general, the purpose of the salt bridge is to keep charge balance on both sides of the compartments, because on one side you're making cations, the other one you're consuming cations, so you need everything to stay charge balanced. So typically these are the spectator ions that are moving through the salt bridge in order for stuff to remain charge balanced. In general, the anions travel towards the anode and the cations travel towards the cathode. So what I mean by anions may be something like sodium plus, that's within the solution, or chloride minus. Wait, sorry, wrong way. Anions, so like chloride will travel through to the anode and sodium will travel towards the cathode within there. Let's think about why. Anions are negatively charged. They travel in order for things to remain charge balanced towards the anode, which is weird, right? Because we said, oh, anode, that's negatively charged, right? That's the negative sign. Why do anions travel that way? Think about what's happening in the solution. on the anode side of our reaction, we are consuming, what are we consuming? We're consuming zinc solid. So we're making what in solution? We're making, in this side of our compartment, our anode compartment, we're making zinc 2+. So every time we make zinc 2+, doesn't the positive charge increase? So in order for it to remain charge balanced, anions have to travel to that compartment to not neutralize, but like to charge balance all that positive charge that's being produced. Does that make sense? Kind of? Yes. So because we're producing, what I like to think about it is we're making, the reaction is making zinc 2+ on the anode side, so those chloride ions not neutralize it, but charge balance it as you're making more zinc 2+. You're making it more positively charged, so you balance it out with negatively charged things. All right, so the other side, cations travel towards the cathode in the solution. So let's think about what's happening on the cathode side. So on the cathode side, we are taking copper 2+, so a cation, and we're making it neutral. So won't the overall charge on the cathode side, won't it become less and less positive as copper 2+ is being consumed? So we're replacing that with other positively charged things. So that's how you kind of think about migration of anions versus cations. And so this basically works true all the time. Anions will typically travel towards the anode, cations towards the cathode, and it's because of the reaction that's actually happening. So cations towards the cathode because we are consuming Cu2+. Each time we consume a cation, we need to replace it with cations to keep it the same charge. Okay, so those are the details of what's going on in a cell. So if I set this up, I have a 1 molarity solution of zinc chloride, 1 molarity solution of copper chloride. I have a zinc anode, a copper cathode. If those two things are separated and I don't connect the voltmeter, nothing will happen because I have no pathway for those electrons to travel. But once I connect it to our voltmeter, we will measure an actual cell potential. And so now I'll talk about voltage and how that plays into these voltaic cells. This is what allows us to predict whether something is spontaneous or not. When you set up these cells and you plug it into the voltmeter and you see a positive number pop up, it means that electrons are spontaneously moving from one cell to another. That's a spontaneous reaction. So how we measure voltage is we need to, as scientists, come up with a scale that allows us to think about, okay, what is like the oxidative power or reductive power of certain substances. So this is where we get the numbers on our standard potential table, instead of just thinking about the activity series where everything is just kind of like, in order, but there are no numbers involved. So we need to reference ourselves. So what you noted on the activity series is that hydrogen was highlighted. And what we saw on the elements above hydrogen, those were easily oxidized. Things on the bottom weren't very easily oxidized. So the same idea here, hydrogen is kind of like our focal point, our reference point. We set the reduction of hydrogen, so H+ to hydrogen gas, as our 0 set point. And basically we reference everything above and below that. Positive values of reduction potential, these things are more easily reduced than hydrogen. The things on the bottom here are less easily reduced by hydrogen. So how do we actually measure this reaction? All right, this redox reaction. So in our previous example with like copper 2+ and copper solid, you could clearly see, oh, copper solid was the electrode, like the cathode or whatever, and we dunked it into a solution of copper 2+ cations. With our standard hydrogen electrode, this is how we set the 0. It's a little bit more complicated because if we look at this reaction, yes, we have hydrogen plus cation floating around, so we have a pretty acidic solution, but we have hydrogen gas. Can you make a gas an electrode? Can a gas be an electrode? No, it can't. It can't. It needs to be the electrode needs to be a solid. So to get around that, we use a metal that can just act as a place for electron transfer to occur, but it's not actually participating in the reaction. So this is where we use platinum. Platinum metal is just acting as the electrode, a place for the hydrogen gas and the H plus to like meet with one another. So like electron transfer can occur. Right? So that's what we see here in this standard hydrogen electrode. So this is the conditions of it. We have a very acidic H plus solution. We have a platinum wire. This is our platinum wire, PT wire, and this is filled with H2 gas at 1 atmosphere. All right, and so what we'll see here is that down here on the platinum wire, the redox reaction is occurring where H plus is migrating to the platinum and electron transfer is occurring. So whatever voltage that reads is our zero. We set that as the 0 mark. Right, whatever amount of potential that requires for this reaction to happen. So we set that as 0. And then everything else we reference to that. And that's how we make up this scale. So this setup is actually really difficult to do, okay? You have gases involved, you have really acidic, so this is a pH 0 solution, like it's really difficult to set up. But the great thing is that once we have all of these values, these table values, like we don't actually have to ever set up this reaction when we use these table values. And we'll see that in a little bit. So this is only a half reaction. So this standard hydrogen electrode is only one part of our voltaic cell. Like if we go back up here, if we wanted to do this reaction between like zinc and H plus, zinc and hydrogen, we would have to replace one of these electrodes with that standard hydrogen electrode. And that's really difficult to do. So let's see how we can't get the other values off of our standard reduction potential table using hydrogen. So that's kind of what you see here. This is another experiment. Oh, I already explained it, where I just swapped out my cathode with the standard hydrogen electrode setup. And so what that allows us to do is set a 0 point. If we say that the reduction potential of the cathode is 0, then whatever I measure when I do this experiment gives me the reduction potential for the other thing. So that in that case, it's whatever is happening at the anode, which is the zinc reaction. So yeah, what I just did is I replaced that copper cathode with my standard hydrogen electrode. So basically what comes out of here is this equation. This is what you need to know. When you set up a redox reaction where we have an anode and a cathode compartment, to calculate the standard reduction or the standard cell potential, or sometimes it's called EMF or EMF, or that's what my brain says, EMF, or cell potential, we can use the numbers from that table to predict what is the potential of that cell at standard conditions. That's the important thing here, at standard conditions. So we can use that table for any type of redox reaction, which is great. So how we go about this is, remember, we defined what's happening at the cathode as the hydrogen reduction. We set that as scientists, we say that is 0. That is 0 volts. So if we do this experiment and we actually measure, like our actual measured cell potential of this setup at standard conditions is 0.76 volts. That is what this value is. The total voltage of the cell is 0.76 equals the reduction potential at the cathode. So look, what is at the cathode? Hydrogen. That is defined as 0. That's defined as 0. So that just requires us to calculate what's the other component. What does that other component have to be? And so minus the reduction potential of my anode. And so in this case, it's my zinc my zinc couple within here. So when you solve for this, you're able to get the reduction potential of that missing piece that we have. So I have that right here. When you solve for the reduction potential of your anode, that's what you get right here, negative 0.76 volts. And that's because we set the cathode as our standard hydrogen electrode, which is defined at 0. And so because zinc is our anode, here, when we calculate cell potential, it is always the reduction potential of the cathode minus the reduction potential of your anode, always. Cathode minus anode, both of them are in reduction potentials. So typically what happens is that whatever value is your anode is typically you're subtracting a negative number, because that's what happens here. So this is our reduction potential of our anode. So if you plug this number back into our cell potential equation, it's 0 minus negative 0.76. So you get a positive 7.6 out of this. So do recognize that the anode, you're doing the oxidative reaction. So that's, you can think of the reverse reaction of your reduction reaction. So that's why we have this negative sign within there, because it flips the sign of your reduction potential of your anode. All right, so you'll see it with practice. You'll oftentimes see a big negative number in what you're subtracting, so you get a positive cell value out. All right, so that's how we put it together. All right, so some group of scientists went in for you to calculate table values of standard reduction potentials for a lot of different substances for you, which is great. This is what we'll be referring to. You never have to do it yourself. All right, so to reference you, our 0 point here of hydrogen, right here. So basically what you see here are a bunch of positive reduction potentials. These materials are reduce easier, more readily, more spontaneously than H+, than acid goes to hydrogen gas. So oftentimes what you'll see are that these substances are the cathode, typically. So these substances are typically the cathode versus something like down here, these substances are typically your anode because they're not great at being reduced. They're better being oxidized, so they will be your anode instead. And so when you think about this equation, E cell is your cathode minus your anode, you get the highest, most positive number when you take a negative number and subtract a large, or sorry, when you take a positive number, so a positive reduction potential of your cathode, minus a large negative number of your anode. That's how we get the largest, most positive cell potential for that to be spontaneous. So yeah, what we see here is that metals are usually, these are the metals that are usually the anode, and they're being oxidized, so it's the reverse reaction. All right, let's see if we can't put this together. So using this, all of these pictures, let's see if we can't determine the relative positions of copper, zinc, and hydrogen in terms of their standard reduction potential. So let's just calculate. Let's calculate their standard reduction potentials for copper 2+, zinc 2+, and H+. Is there one we already know? The standard reduction potential for those three things. Is there one we already know? Hydrogen is 0. Yeah, so there's one already. So that's 0. So E reduction of our hydrogen friend is 0. 0 volts. So we have two experiments here. We have an experiment between zinc and hydrogen, and then we have an experiment between zinc and copper. Zinc and copper. So let's see if we can't calculate these reduction potentials of copper and zinc based upon these experiments. So the equation we're using is your overall cell potential. So this is what we measure. This is what we measure in these experiments. See how these are measured right here? Is equal to your cell potential, or sorry, no, your reduction potential of your cathode minus the reduction potential of your anode. So we just need to be a little bit clever here and realize, okay, what's my anode, what's my cathode? But thankfully, all of these pictures are always drawn how? Anode, cathode, alphabetical order. So in this first experiment, zinc is my anode. My hydrogen, that is my cathode. So for experiment one, if we set up this equation, your cell potential that's measured, isn't that 0.76 volts? Now we need to plug in the things we know and we don't know. Its cell potential equals what's at the cathode minus what's at the anode. So what's at the cathode? Hydrogen. We know that one already. That one is 0 because it's the hydrogen. That's at the cathode. Versus the anode, that's zinc. So that's the piece of information that we need to figure out. So that's the reduction potential of my zinc couple that I'm trying to calculate. All right, and so what we get is that reduction potential of zinc, because that's what's at the anode, is negative 0.76 volts. Didn't we just do that on the last slide? I think we just did. We did. But based upon this answer, now we have the reduction potential of zinc, and that will come in handy on experiment 2 because zinc is what? Zinc is the anode again. So that allows us to fill in that blank for zinc, allowing us to calculate, okay, what is the potential, the cell or reduction potential for the missing piece, which is copper in that case. So let's look at experiment 2. All right, experiment 2, again, we're doing cathode minus anode again. All right, your cell potential equals your reduction potential for your cathode minus your reduction potential for your anode. So the measured E cell is 1.10 volts. That's what's on the voltmeter. Oh, geez. That's what's on the voltmeter. That's the measured cell potential. So what is at the cathode? Copper. That's what we're trying to figure out. That's the missing piece that we don't have. So I'm just going to put E red copper, because that's what's at the cathode, minus whatever's at the anode. So this is your zinc anode. So we are going to subtract the number that we just calculated. So minus negative 0.76 volts. All right, and so what you get here, so this becomes a positive number, so just subtract 1.1 minus 0.76. So the reduction potential of your copper equals 0.34 volts. So that's for copper. This one's for copper. This one is for zinc. And then we already know that hydrogen is, its reduction potential is 0, because we defined it that way. So if we put these in order now, what substance is most easily reduced? Which substance most spontaneously is reduced? Zinc, yes, because it has the highest reduction potential. Yes, so here it would be zinc 2 plus. So I'm going to write most easily reduced. Oh, wait, no, it's not zinc. Sorry, it's not. It's the most positive reduction potential is the thing that is most easily reduced. So it would be copper. I'm sorry, I forgot the numbers here. So it would be copper 2 plus is most easily reduced. These are reduction potentials, so you want the positive E number, the positive number. Yeah. Next would be, what substance would be next easily reduced? Hydrogen, yeah. So technically it's H plus. We're reducing that to H0. So that would be next, and then next up would be the negative cell potential, zinc 2 plus. Zinc 2 plus is better to be oxidized. Because of the negative reduction potential. It's better to be oxidized. So let's look at this scaling and see if it doesn't match the table on the previous slide right here. Does it match? Does it match? Where's copper? Right there. Right, there's copper, hydrogen, zinc. Is that what we just said? Yes, that's what we just said. That copper is more easily reduced, zinc not so much. So it matches exactly with the table based upon these fake experimental datas. Okay, so let's do another one. Okay, based upon this voltaic cell, so these two things, these two redox reactions, what is the standard potential of the cell? And let's sketch the cell. So I give you appendix, I don't think it's C, I actually think it's appendix E, whatever, standard reduction data. So it's the same table that I talked about before. So those are the reduction potentials of those two half reactions, reduction half reactions. So based upon this data, what is the overall cell potential when we connect those two things together? So the strategy here is we are using this equation again. We are using the overall measured cell potential equals whatever's happening at the cathode and whatever's happening at the anode. But we need to, the thing is I didn't tell you what's the cathode and what's the anode, so we need to be smart about it. We need to be smart about it. The cathode is the thing that is reduced. So what substance is more easily reduced? Tin. Yes, because it's less negative. It's the most positive number, although both of them are negative. All right, so tin is much more likely to be reduced. So this is the reaction that's happening at my cathode because it has the most positive reduction potential. Then what substance is most likely to be oxidized? It's the substance that has the most negative reduction potential because that's not super favorable, so it's better to just do the reverse reaction instead. So cadmium solid is more likely to be oxidized. So that is your anode. Doing this, recognizing that you want the most positive the most positive reduction potential to be your cathode and the most negative cell potential, let me rephrase that. If you recognize that if you identify the substance being reduced at the cathode is the most positive number, right? That's the first number within here, if it's the most positive, and you subtract the most negative value for reduction potential for your anode, that's how you get the most positive value for your cell potential, when you subtract a big negative number. So let's actually do that now, putting that together. E overall cell equals your, I'm just gonna write cathode minus anode. So just plugging in those numbers straight as we identified it, it's negative 0.14 volts minus negative 0.40 volts equals positive 0.26 volts is your standard cell potential. So based upon the sign of the overall reaction, is this a spontaneous reaction? Or does this redox reaction happen spontaneously? Yes, it does. When we hook up these two cells together and we plug in that voltmeter, we'll see, boop, a positive number pop up, meaning that electrons are being transferred spontaneously. Even though both of these are negative numbers, right? And then how we set it up, we need to be smart in how we identify what's the cathode or the anode. Me personally, I just think, okay, how do I set up these numbers in such a way to make everything positive, to make that E cell as positive as possible? So let's sketch the cell. So we always draw the anode on the left and the cathode on the right. So what half reaction is happening at the anode? The cadmium. So I'm gonna have my cadmium solid electrode here, and it's floating in some cadmium 2+ solution. All right, and then my cathode on the other side, that's my reduction reaction. So I'm going to have tin solid as my electrode, and I have tin 2+, SN 2+, floating around in my solution. I connect those by my voltmeter. What's missing? What's missing? Salt bridge. Yeah, if you track where the electrons are going, right, you're losing electrons at your anode, they're traveling to the cathode, but you have to complete the circuit. So how we complete the circuit is with the salt bridge. So I just draw like a little umbrella thing to connect them. See, okay, I don't think you guys will ever make a electrochemical cell that looks like this. It's like really easy for me to draw these things. It's actually really hard to do this in practice. I did have to make one electrochemical cell where I had to make a salt bridge. And what you have to do is you have to take these like U-shaped things and you have to mix agar or like gelatin with salt. And then you have to like make jello in the tube. And that's your salt bridge. So you need something that's like a gelatin, right, to be like solid, but it has to be able to move ions. So you have to like mix salt with it. It was really gross because I had to like microwave it. And then you invert it and you put it in the two solutions. So it's a lot more steps than just how we draw it like this. So that is our cell. So let's, but before, I want to look at this fully, all right? So we know that on this side, on the left side, we have the anode, and on the right side, we have the cathode. We know that electrons are going from anode to cathode. We know how the cations and anions in the salt bridge are moving to remain charge balanced. Let's see if we can't write the overall balanced equation, the overall balanced redox reaction that's occurring. So looking at the two half reactions, we have reduction and oxidation. Can I just add these two reactions together to get a balanced chemical equation? No, because what's wrong? The electrons don't cancel. They're both on the same side. So what do we have to do? These are both reduction potentials, but isn't one of these reactions, it's the oxidizing reactions? What's being oxidized? The cadmium. So in order to write the balanced equation, we actually have to flip this reaction, just the balanced reaction, in order to add those two up. So the overall balanced reaction here is tin 2+ plus cadmium solid gives us, what's it, tin solid plus cadmium 2+. That's what's happening here? Yes. So what I did is I just, in my mind, flipped this, whatever the oxidation reaction is happening. So the two electrons are on the other side, so they cancel out and you can add them up. And so if we kind of look at that reaction, what's happening as time progresses, as electrons are being transferred, isn't cadmium solid being consumed? So what we see here is that the anode is being eaten away, right? Like the mass of the anode will go down. Versus over time, as we're transferring electrons, the mass of the tin electrode on the cathode is increasing. And that's the exact same what we looked at the previous example with like zinc and copper. And so it's the same idea here. The anode is losing mass while the cathode is gaining mass. So that balanced reaction is consistent with what we see. And so the last thing here with this question is we can write this, yeah, this is a lot of work to write this, sketch this cell, but we can also write line notation to represent the same thing. So how we write line notation is kind of similar in where you draw, you write all the stuff in the anode and you draw this double line to mean salt bridge, and then you draw all the stuff in the cathode. or you write the substances present in the cathode in their proper states. So how you use line notation is that you write the anode, the substance that is the anode. So in this case, it's cadmium solid. And because there's a phase barrier, we have a solid in contact with something that's aqueous. We write cadmium 2+ aqueous. Then we draw everything that's in the cathode. So we draw the salt bridge, which is the double line. And then we write tin 2+ aqueous because it's in the aqueous phase. And so we're trying to say, hey, these two aqueous solutions are separated by the salt bridge. And then we draw a phase line and represent tin solid to represent the cathode. So this is like an easier way to draw the actual cell diagram. They mean the same exact thing. And what's really great is I like line notation because you can really easily calculate cell potentials. You can really easily calculate cell potentials because remember, a cell potential is just the cathode minus the anode. This is the cathode, that's the anode. I just look up those values and just subtract them. All right. Okay. So without doing any calculations, if you were given these three reactions, what combination will give you the largest cell potential? What substance is being reduced? What substance is being oxidized? Which one will give you the most positive cell potential? What is at our cathode? What's at our cathode? The first one, the second one, or the third one? Cathode is what reaction? Reduction. So yeah, we're looking for the most positive reduction potential. So this IO minus business, that reaction will be our reduction. That's going to be our cathode. What reaction will be our anode? 1, yes, because it's the most negative. So that is our anode. That's the reaction where oxidation occurs. All right. And so, yeah, so then we just go to town and calculate it. So cell potential equals the reduction potential at the cathode, so 0.49 minus the reduction potential of whatever's at the anode, so minus negative 0.86. This is the combination that gives us the most positive value, and so this is 1.35 volts. Okay. So what is the overall balanced reaction for this cell? So we're not using the second one. We're just looking at the first one and the third one. So they're both written in reduction potential. So just like in the previous one, we need to manipulate these reactions a little bit before we can add them up. Thankfully, these are already balanced half reactions. So the only thing we need to do is make sure what match before we add them up. The number of electrons. So in your mind, which reaction are you going to flip? The first one or the third one? The first one, because that's oxidation. So flipping that first one puts the 3 electrons on the other side. All right. But then the idea here is that we need electrons to cancel. So what value do you need to multiply them by? The first one by 2 and the second one by 3. So just because we multiply before we add up these reactions, we actually do not change the cell potentials at all. All right, so the cell potentials that we use, these reduction potentials, just are based upon the identity of what's being oxidized and reduced. So remember, like when we did Hess's law and we multiplied a reaction, we had to do the same thing to delta H. Remember that? Cell potentials do not follow that rule. So just because we multiply that second reaction by 2 doesn't mean we change the reduction potential by 2. All right, so cell potentials are untouched in that case. Okay, So what I'm trying to say is that you don't have to balance a redox reaction to calculate the cell potential. As long as you know the components, then you're good to go. All right, I'm just gonna end there. So combine these two reactions where you flip one, take care of the coefficients, make sure electrons balance, and we will pick up on Wednesday.